Gas considerations. Gas, described in more detail in the gas section, is an incredibly important consideration in smart contract programming. Gas is a resource constraining the maximum amount of computation that Ethereum will allow a transaction to consume. If the gas limit is exceeded during computation, the following series of events occurs. 1. An out-of-gas exception is thrown. 2. The state of the contract prior to execution is restored. 3. All ether used to pay for the gas is taken as a transaction fee. It is not refunded. Because gas is paid by the user who initiates the transaction, users are discouraged from calling functions that have a high gas cost. It is thus in the programmer's best interest to minimize the gas costs of a contract's functions. To this end, there are certain practices that are recommended when constructing smart contracts so as to minimize the gas cost of a function call. Avoid dynamically sized arrays. Any loop through a dynamically sized array where a function performs operation on each element or searches for a particular element introduces the risk of using too much gas. Indeed, the contract may run out of gas before finding the desired result, or before acting on every element, thus wasting time and ether without giving any result at all. Avoid calls to other contracts. Calling other contracts, especially when the gas cost of their functions is not known, introduces the risk of running out of gas. Avoid using libraries that are not well tested and broadly used. The less scrutiny a library has received from other programmers, the greater the risk of using it. Estimating gas costs. If you need to estimate the gas necessary to execute a certain method of a contract, considering its arguments, you could use the following procedure. Variable contract equals web3.eth.contract of ABI .at of address. Variable gas estimate equals contract.myAwesomeMethod.estimate gas with 3 arguments, arg1, arg2, and from accounts. Estimate gas will tell you the number of gas units needed for its execution. It is an estimate because of the Turing completeness of the EVM. It is relatively trivial to create a function that would take vastly different amounts of gas to execute different calls. Even production code can change execution paths in subtle ways, resulting in hugely different gas costs from one call to the next. However, most functions are sensible, and estimate gas will give a good estimate most of the time. To obtain the gas price from the network, you can use variable gas price equals web3.eth.getGasPrice with no argument. And from there, you can estimate the gas cost. Variable gas cost in ether equals web3.utils.fromWay with 2 arguments, gas estimate times gas price, and a string that spells ether. Let's apply our gas estimation functions to estimating the gas cost of our faucet example, using the code from the book's repository. Start trouble in development mode, and execute the JavaScript file in the gasestimates.js example. First, set the faucet contract variable to artifacts.require of faucet.sol. Second, call faucetContracts.web3.eth.gasPrice with a callback function that prints out the resulting gas price. Within the same callback function, run faucetContracts.deployed with a callback function that takes the resulting faucet contract instance and call faucetContractInstance.send 1 ether, followed by another call of faucetContractInstance.withdraw.estimate gas of 0.1 ether. Return this gas value and process the return value in the next callback by printing out this gas value as the gas estimation, and then printing out the gas cost estimation by multiplying this gas value times the gas price. Here is what that looks like in the Truffle development console. 1. Truffle develop. 2. Exec gas_estimates.js. Output. Gas price is 2 times 10 to the 9th power Wei. Gas estimation equals 31397 units. Gas cost estimation equals 0.000629794 Ether. It is recommended that you evaluate the gas cost of functions as part of your development workflow to avoid any surprises when deploying contracts to the mainnet. Conclusions. In this chapter, we started working with smart contracts in detail and explored the Solidity contract programming language. We took a simple example contract, faucet.sol, and gradually improved it, and made it more complex, using it to explore various aspects of the Solidity language. In the Viper chapter, we will work with Viper, another contract-oriented programming language. We will compare Viper to Solidity, showing some of the differences in the design of these two languages and deepening our understanding of smart contract programming.